Good afternoon, everyone, and thank you for joining our webinar today. My name is Megan Gorman, and I am a Customer Engagement Specialist for TestOil. We are very pleased to be hosting this webinar titled Why Equipment Fails. Before we start the webinar, there are a few things I want to go over. First of all, let me check my audio. If you can hear me, please raise your hand by clicking on the little hand icon in the toolbar on your GoToWebinar application. Great, I see that. Awesome. Thank you. It looks like my audio is working. Now, the other thing I wanted to do is let you know that everybody will be on mute during this webinar. We are recording this webinar so I can share with you later on, and by keeping everyone muted, we will ensure a high-quality recording for today. If you have any questions, you can submit them using the questions field in the toolbar on your GoToWebinar application. If we have time at the end of the webinar, we will address your questions. If we do not have time, we will address questions via email. Okay, let's get started. So as I mentioned, today's presenter is Terry Harris. Terry Harris is a certified maintenance and reliability professional certified through the Society of Maintenance and Reliability Professionals. He has worked in the manufacturing process industry for 26 years for a Fortune 100 company. Most of his time was devoted to maintenance area efforts, with most of his career being devoted to improving the reliability of his plants and other U.S. and European locations. Along with working as the facility maintenance and reliability leader, Mr. Harris was involved with many corporate-wide projects to cut costs and improve equipment reliability. For many years, Mr. Harris has devoted his efforts in applying his knowledge to critical pieces of equipment and processes within many industries with excellent results. Mr. Harris has performed training in the U.S., Europe, China, Singapore, Thailand, Canada, and Korea. Thank you for joining us today, Terry Harris. I'm going to pass the controls on to you now.
All right, thank you, Megan, and welcome to everybody. I'm glad you took some time out of your schedule this afternoon or at lunchtime here to listen to the webinar. I hope you find some good information, and if you need a copy of the webinar afterwards in a PDF form, I'll get that to Insight, and also you could email me at this email address here to get a copy of that. And hopefully there's some information here that can help your processes. A little bit, Megan was telling you a little bit about myself. I've actually done this training or some reliability training of some kind in 22 different countries around the world now. And you can see I've got quite a few different training programs we do for companies in predictive and proactive maintenance. I do some RCM facilitation. I have an RCM database which I teach people how to do that in a cost-effective way. One of the key areas we train on is lubrication audits and lubrication training programs, teaching people how to take samples of the lubricants, how to actually read those reports and know how long the lubricants are going to last. And again, the key thing there is knowing how long your equipment's going to last based on what the lubricant quality is. And that's why I work so closely with Insight in those areas. But you can see a lot of other programs there with maintenance and PM type training. And then we build some lube storage and filtration rooms and equipment for the industry also. So just a little bit about myself in this slide here. You know, I do all my training based off the PF curve, or if you look at the right side of this curve, you'll see the area over here where people find out about failures with human senses. You know, components or bearings are getting hot. We can feel something moving. We have noise. If we're doing all of our maintenance, we're finding out about our failures of our equipment in this area, you're very reactive, and you're only going to be about 10 to 20% effective or efficient maintenance. Whereas we move into our predictive technologies area in the center of the PF curve, you can see that as we use the technologies, you know, such as mechanical ultrasound, vibration analysis, oil analysis, as we use these technologies effectively and actually react to them, we can solve a lot of our problems or correct the issues before the equipment actually fails. So if you take the example of oil analysis, if we monitor our lubricants closely, and we know when we have high particle counts, we know when the lubricants oxidize, and we change or filter those lubricants at an early stage, the equipment can last many, many more life cycles, and I'm talking about 3 to 10 times longer. Then over on the left-hand side of this curve, the proactive area. You know, doing things in this proactive area can make your equipment last longer because we're doing these things when the equipment's newer and it's rebuilt its peak performance stage. So, to understand lubrication excellence, precision alignment, precision balance. And we're going to talk a little bit about this select supplier, buying the most reliable components for your critical equipment. Then you can see there's things down here like the equipment ranking. What is your critical equipment? And how do you know when to put those components on there? How do you know what equipment you should do predictive technologies on? So a lot of things in the left-hand side of the column to make your equipment last many more life cycles if you're using in some or most of these processes and methods. So what's reliability? Reliability is reducing the chance of a failure of equipment by eliminating failure modes of the components. Now, a lot of times when I walk through plants and I see motors in a maintenance shop, or I see a gearbox there, and I ask why those components failed, they'll get answers like, well, it locked up, or the gear stripped out, or the bearings failed in the gearbox. But we have to know exactly what component failed in that piece of equipment to understand how the equipment actually failed, and then from that information, we can keep those components lasting longer and extend the life of those pieces of equipment. So why is reliability important? If you're talking about reliability issues, whether you're a vendor, whether you're a plant operating plant, whether you're in operations, equipment reliability ensures that the equipment will last many more life cycles longer, and it reduces the cost of ownership and the life cycle cost of the maintenance. And we'll talk a little bit about life cycle cost as we go through this presentation, because it's important to understand the life cycle of your equipment and how, as reliability engineers or operations people, we need to extend that life cycle. Here's an accepted belief. I've got this bearing scatter chart here. This was done in 1985, which shows a group of 30 identical bearings ran at the same identical load with the same lubricant, the same speed, and look at the failure rates of these bearings. Now, why did they fail at different millions of revolutions? You can see some failed at 5 million revolutions, and we had one bearing that made it to 300 million revolutions. So why did that happen? Well, from this chart in 85, they assumed that bearings were random failures. There was no way to extend the life of the bearing. We just had to use predictive technologies to find out when it's going to fail. But through some of the things we'll talk about today and through my training course on the failure modes of equipment in RCM, I show you different ways to make these bearings last longer life cycles. Now, fortunately, there's a company in New Zealand that's redoing this study in modern days here, and they're going to do 90 bearings over 3 years, so we'll have some different data here in a few years. But if we accept this as an accepted practice, we're not going to have very good reliability at your plant. So it's important to understand that equipment and components can last and function many more life cycles. A lot of people believe, and I go into plants all the time, where they change motors out based on mean time between failure. They change out belts and bearings based on mean time between failure because they assume that's all the longer it can last. But there's many things we can do to make those components last the longer life cycles. So let's talk about why some components fail. So why is reliability important? Well, if you're a vendor, it's customer satisfaction. If you're a maintenance person, it's a lower cost of maintenance, longer equipment life cycles. If we catch components with our predictive technologies at an early stage, there's less risk of collateral damage. There's less risk of customer downtime. We're going to lower our maintenance labor costs. There's less risk of environmental health and safety exposure. And you're going to have some future sales success stories here. It has a payback. The company I came from, Cargill, when we started doing reliability, one of the things that happened as the equipment started operating better and longer life cycles, we actually started producing more rate. We had less quality issues. We had less environmental health and safety issues, and all those factors resulted in more money to the bottom line. So what's it worth? Reliability sometimes has a 10 to 30, has a big value in what it's worth. It's worth 10 to 30% more to all the designed, built, and sold equipment. So if you're a vendor, you can guarantee equipment not to fail for a longer period of time. Now, unfortunately, a lot of our vendors who are making motors or making bearings and making our equipment don't want it to last forever because they like to sell spare parts. So we, as people who buy stuff and determine how things fail, and we want things to last longer, we have to know some of these details here that we're going to talk about in the next 30 minutes. So if you're a vendor, your customer telling your customers, or if you're an installer, and I did this kind of work for a few years where I'd go in and install pumps and fans and rotating equipment for companies, and I would guarantee no failures for 3 years. Now, how can you do that? Well, again, we're going to look at some methods here in the next few slides where I can go in and make those guarantees. Now, I've never had to pay off one of my guarantees for the 3-year failures because we do things right up front. So what are the factors that go into equipment life cycle improvement? Well, we have engineering, we have the design step, we have fabrication, we have the installation step that we were putting our equipment in, and then we have operations who operate the equipment, we have maintenance who maintains the equipment. So what are the factors? These are all the factors that improve our equipment life cycles, but these are also all the factors that cause our equipment components to fail. So if we look at engineering issues, and these statistics were from a number of different organizations, including Cargill, where we looked at why equipment fails. So look at this one here, 25 to 35% of all equipment reliability issues are engineering and design related. Poor equipment selection, not selecting the correct pump or the correct motor. Now a lot of people say, well, what's the difference in motors? Well, in a study we did with Cargill, we found out that there's a couple motor vendors that make better motors that'll last longer than other vendors. One of those examples is Toshiba. The reason their motors last longer is because the balance standard is much better on the rotor. They balance their rotors to 0.05 inches per second, where all your other motor manufacturers balance to an ESA or an ANSI range of 0.08 to 0.12. But many of the motors I check out of the box in new equipment are much worse than that balance standard. I've checked brand new motors from Reliance out of the box that were 0.28 in balance. Well, those motors are only going to last about a year when that happens. But a lot of times we don't check new equipment for balance because we assume it's new. Improper sizing of equipment components, improper design practices, with pipe steering, torque methods on fasteners not being proper, poor or proper base foundation, the structures we put our equipment on. Not understanding factory alignment. I was installing equipment for a company, and I asked about the alignment procedure after the equipment was installed, and they said, oh, we align all the equipment at the factory. Well, it's not aligned and balanced when you get it in the facility. And then finding out who makes the best motor, who makes the best pump, who makes the cleanest lubricants we're going to put in our equipment, and all these other components. I just listed a few here for different industries. Who makes the best of those? And then the question is, when you know who makes the best, do you put the best equipment on everything? And the answer is no. The answer to that is you put those best components, those best motors, pumps, and couplings on your equipment that has the highest criticality. And once you start correcting the issues with that equipment, your failures and your downtime are going to be reduced. So when do you purchase for the best motor? You purchase it for your high criticality equipment. And that's another webinar that we'll do later on in the year on equipment criticality. And here's an example of equipment criticality. You take this 1972 Ford pickup, and it's got these components in it: wipers, headlights, brakes, tires, seat belts, and a fuel pump. What's the most critical component on that Ford pickup truck? You can go down through, and if I ask 10 different people, they'll give me different answers. Somebody will say that maybe the tires are the most critical component. Some people say the fuel pump, because without the fuel pump we can't operate. But if you're from a safety background, maybe you say it's the seat belt. We can't operate the truck if the seat belt's ineffective. We got to have brakes. But it's dependent on how you use the equipment as to which one of these components is the most critical. If you're in an area where it never rains, like maybe El Centro, California, where they say it rains one day a year, you may not need windshield wipers. If you never drive the truck at night, you may not need headlights. So again, it's dependent on the application, but it's having a process to determine what components in your plant are the most critical. And then once we find out, we put the best equipment on those critical components. And these are all people that participate in an asset criticality. Your safety, environmental people, your commercial people, operations and maintenance all have to have an input into criticality. When you do criticality, it can't just be a maintenance team determining what equipment or what equipment components are critical. Here's an example of my asset criticality database where you ask the questions. And as you go along, you can see this overall score as we ask the questions in all these areas of safety, environmental, sometimes food safety, quality and operations. The database actually keeps track of where we're at here on the scoring, and it gives us overall total. And from the overall total, we can determine what equipment in our plants is the most critical. Now, considerations for design. How do you design things? Do we want to make everything last for 30 years? Who's the customer? How critical is the customer? How critical is our operation? How much safety is involved? Are you maintaining the equipment yourself? So you start asking these questions. How important is it to engineer and design for long life? Is equipment cost a consideration? Is downtime a consideration? So a lot of factors. When you're trying to do precision alignment, what base should you have under the equipment? If you look at the base in the upper left-hand corner, you can't really get precision alignment on that one because it's not a perfectly machined surface. Where the other two they show here have machined surfaces to set the motor, to set the pump, and we can actually obtain precision alignment on those components and add 3 to 5 times life. Here's something that we looked at that people don't consider when you're buying a pump. What's the shaft deflection going to be if somebody slams the discharge valve shut? Well, here's a calculation. There's something called the L3D4, and this is known by most pump manufacturers, but they never bring it up because of one reason. They like to sell pumps and pump parts, but your L3D4 should never be over 50. So it just gives you an example here from the pump we just looked at. From the impeller to the bearing is 7 inches. We take that to the third. The shaft diameter is 1 7/8 inches. So we have an L3D4 ratio of 27.8, a well-designed pump. Now, if we cut the shaft down to put a shaft sleeve on, we cut the shaft down to 1.5 inches for the shaft sleeve. Now our L3D4 goes to 68.6, and it's not a very reliable pump. That shaft's going to bend sometimes on startup, sometimes when people close discharge valves too quickly. So again, just a little quick review of different things you look at in design and engineering. So when do we want to use the best? We talked about that. Look at your life cycle cost. Is it something, if you're selling equipment, can you sell life cycle cost? I put a couple slides in here. Here's a slide of a Toshiba motor. And Toshiba motor shows the life cycle cost, a 20-year life cycle cost, which is usually their 10. But you can see the initial cost of a Toshiba motor if you're talking about, and the reason I put this slide in here, because a lot of times companies say, I'm not going to buy a Toshiba motor because they're 30% more than a Siemens motor. Well, why are they 30% more? Well, they got better balance standards. They got better insulation. They got better windings. They mill the feed off on the bottom of the motor to 1/1000th after the motor's built to help alignment processes. But you can see even spending 30% more, the initial cost is only 1% of the life cycle cost. Here's just one. I always ask people, what do your shoes cost? Well, you really don't know what your shoes cost. You don't know what your car cost until you actually sell it or get rid of it. If you keep track of all those costs, all we know is what we pay for it. It's the same thing when you buy equipment in your plant. You only know what you pay for it. So, but if you buy the better equipment, you can see on this pump life cycle cost, the pump purchase cost is the smallest piece of the pie over a 10-year life cycle cost. You have your installation cost, you have maintenance cost, you have operating and engineering or energy cost. Look, so again, the pump cost is the small piece of the pie. So buy the better pump. Now we get into fabrication, the way people make your equipment, the structures that it sets on. So you can have improper piping practices, elbows and inlet flanges, pipe strain, improper welding methods, improper torque methods on fasteners. You have to ask these questions during fabrication. Your fabrication procedures down here with unlevel base structures, improper lack of anchoring points. A lot of these things happen in real life. The way people ship things to you, your equipment, over-tensioning equipment, tie-downs, the way we move it, the way it's going across rough roads, can it be damaged and affect the fabrication? Defective new parts or components. I've seen this at plants I went to and did studies for how equipment's made at plants, and I find bearings laying out on a table. And at one plant I went to, they were big 6-inch bearings. They were covered with welding dust. I asked about the welding dust when they were assembling the components. They said, well, don't worry about it. We blow it all out. We wash it out with oil. Well, I know from oil analysis you can't get all those particles out, so now we have defective new parts or dirty new parts. Improperly storing parts, before they're installed. Damaging new components from transportation. No specifications for new parts or components. And here we got one here on installation. 15 to 25% of your failures are poor installation practices, improper handling practices by your contractors, improper anchoring practices, not using the proper grout, improper piping practices in the field, coupling alignment issues, no coupling or poor alignment methods being used. How many of our contractors do you really trust that are doing the jobs correctly? Here we have some contractors pulling a piece of pipe in to weld it to a pump. Well, that's going to greatly affect the life of that pump when we do things like that. This was a taken out of power plant in Cincinnati, where they have a 150 horsepower motor. They used a top-of-the-line alignment tool, and this pump was mounted. You can see a 150-horse motor pump mounted on a channel iron base that's a half-inch thick. The bolt doesn't even come through the nut on the back bolt there. So all kinds of bad alignment practices. It's a bad base structure. So that pump is not going to stay in alignment even when it started. That base structure should be as thick as the feet on the pump to be a perfect install and to stay in alignment. You can see the hammer marks here where they beat it into alignment when they're using their laser tool. So again, not good practices. Here's a practice at a plant in Texas where they put a concrete foundation in, they grouted the base in, they used machine surfaces for the motors and the pumps, they used synthetic oil, had good supports on their piping, so this installation is going to last a lot longer. This is actually a balanced rotor in the motor. So you're going to get 3 to 5 years life with no failures out of this component just because of good installation practices. Installation, making sure you use the proper viscosity of lube. Use the right lube. Not putting dirty lube in from your plant. I was at a plant doing an install once, and they brought me the lubricant for the pumps in 2 vinegar jugs. And I had a 3-year no-failure guarantee. I couldn't use that lube. I had to go buy some filtered synthetic lubes for that application. So again, poor lubrication practices. And down here, precision grout, like that installation I showed you on the concrete base, but then they don't use precision alignment. They don't use precision balanced pumps and motors. But whenever you do an installation like that and you make it that base really rigid, where do the forces of imbalance go when the base is really rigid and everything's anchored down like that? They go right directly into the bearings, so you get no extended life. So if you're going to use good structures like that, make sure you use precision alignment, make sure you purchase balanced components. And then how many of your failures come from your installation practices, from maintenance people putting couplings on? The way they install bearings, the way you store bearings. So a lot of installation failures. Now we get down to the equipment here, and we've got operations that are operating the equipment. Well, if we don't operate it correctly, what kind of bad things can you do in operation? But 10 to 20% of your failures from your equipment are from operations. Starting equipment under a full load. If you close the discharge valve too quickly on a centrifugal pump, you can bend the shaft. Your maintenance people or your operations people not trained to go out and touch the equipment and monitor thermal conditions and catch things at an early stage. Your your operations people not trained to go out and touch the equipment to find out if you have physical vibration. Not monitoring your visual oil checks. I train operators in some Owens Corning's plants to look at the oil and tell if the oil is oxidized, so you can report that back to maintenance. Sometimes we can tell if there's moisture in the oil just by a visual check. Operating equipment and manual. Lack of fluid to the pump on startup and destroying seals. All things a lot of times that are happening from operations. I put this one here, water on components. I went to a plant one morning that I was doing some work at, and the motor was kicking out the night before in the thermals, and so the operator thought it would be a good idea to put a water hose on the electric motor. Well, that's not a good practice, but again, they're not trained. It's probably been a common practice at that plant. Lack of a TPM program. Total productive maintenance is where we get operators involved in not just the maintenance of our equipment, but doing proper inspections. One of the things I'm doing with Owens Corning right now is we're doing operator training on equipment failure mode, so the operators can recognize different things that happen on their equipment that cause it to fail. An example of that, if you have a motor and the fan guard's all blocked off on the back of the motor and it's not getting air across the motor, well, this can shorten the life up of that motor by 3 to 4 times. So the operator now cleans the back of the fan guard so we get good airflow. Now we get down to maintenance. So we've got all these inherent failures, all these things that happen before maintenance ever gets control of the equipment. So here, maintenance only has 20 to 30% responsibility for all failures directly contributed to maintenance. But here's how maintenance can fail. Improper inspection of components. Not being trained. Improper lubrication practices. How many of your maintenance people have actually been trained in lubrication to filter the lubes before they put them in? Not to put too much lube in there and create extra heat. Not doing lube analysis, not even knowing how to visually look at the oil and tell if we have a problem. And then you've got no or poor preventive maintenance programs. And I find this at about 80% of the plants I go to where you have maintenance procedures or PM procedures that say, check the pump, check the motor. Well, what does that mean? So, we have to define to have the preventive maintenance tasks be non-subjective. They have to be tasks that tell them what to do. I go to plants all the time where there's no predictive maintenance program. Not using tools. There's a lot of good, reasonably priced tools out there we can do predictive maintenance and tell if things are failing long before the component we can tell physically with our physical senses. So, oil analysis, mechanical ultrasound are nice, cheap, predictive technologies we can use to find out if equipment's failing at an early stage. No report proactive maintenance processes. We looked at all those processes in our system or on our PF curve. Lubrication excellence, precision alignment, precision balance. All these things are proactive tools we use to make our equipment last longer. And then what about training programs? First of all, you have no procedures at your plant, written procedures on how to correctly do our maintenance tasks. We have no training programs. I was even told by a young maintenance supervisor about 2 years ago, I said, what are your training programs for your maintenance staff? And he says, well, I don't have any. He said, these guys all have 20 years experience. What would I train them on? Well, my comment to that was, you're down 50% of the time, so we must not be doing everything correctly, right? So we developed some training programs. And then follow up on those programs and retraining. The training process at a plant, especially for maintenance, never ends. There's all kinds of good training programs, and if you're interested in some of those, let me know. So those results I showed you there, my percentages were done from a study I did with a water company and some things we did in Cargill. But look at this. This comes from the Hartford Steam Boiler Insurance Company. And it says here, almost 50% of work orders are preventable. Engineering and design are responsible for 42%. Operations, 26%. Maintenance, 28%. Are responsible for failures of equipment. Now, they've only got 4% here for management, but you know what? Management's responsible for everything that goes on the plant, so that number should be much, much higher if we're not doing our other things like training and developing operators and procedures. So, but you can see that numbers here are real high. Now, why would an insurance company do this study? Well, insurance companies are tired of paying for failures in our plant, fires and explosions and major equipment failures. And so they're looking into more of these studies of what can we do. So, because there's insurance companies that are going to stop paying for some of the failures at their plant over the years. That's why your deductibles are going up, and so insurance companies are monitoring this very closely. So you can see there's many reasons why our equipment fails, even before we start the equipment the first time. On critical equipment and operations, we need to make sure we design the equipment correctly and we order reliable components on the equipment. So let's say we have a component, or let's say we have a process in your plant. We're going to put a new process or piece of equipment in. We go to the vendor. He gives you a price for that equipment. And then the management style there is to go back to the vendor and try to reduce that price. Well, when you reduce that price, you're going to get cheaper components. So if you're buying equipment, let's say that have bow door motors on there, and if this is a critical operation or a critical part of that machine and you put a Toshiba motor on there, that Toshiba motor is more than likely installed correctly is going to last 3 to 8 times longer than the bow door motor. So again, it's making those decisions. So sometimes the cost of your new equipment is going to be higher, but remember our slides on the life cycle, it's going to last longer. The cost of maintenance is going to be less. So the initial purchase price is going to be the lowest part of that pie. Now, after your equipment's installed, are we performing the correct PMs? Now, sometimes at plants I go to, we start the equipment up, we run it, something fails, and we develop a PM around that failure, a new PM. If you're using the OEM's suggested PMs, some of those, about 30% of those, are ineffective. They don't actually help the equipment component last longer. They don't help you find failures. So you need to look at all your PMs. Ask, how were the PMs developed? Were they from past failures? Were they from OEM-directed instructions? Are you doing PMs that should be PDMs? Here's a question I'll ask, and I find this at many plants when I'm doing maintenance audits. Are the PMs actually getting completed? Now, a lot of times we put out work orders. I go to even major companies where they'll still put a stack of PMs on the maintenance table at the beginning of the week and beginning of the month, say, guys, get these done. Well, if they're not ranked by criticality, do they get them all? Well, really, do they actually get them all done? Are they just pencil whipping some of them and turning them in? Is there a way for you to find out if they get them done? And are they PMs that need to be done? So if we put critical numbers on the PMs to make sure the ones on the critical equipment are always completed, you're going to see some reduced failures. I've got some data from another company I work with that shows as the amount of PMs percent complete was increased, the percent of reactive maintenance decreased. And they're just continually working on that. So they've decreased their reactive maintenance by 27%. They've increased their PMs that are actually getting completed by 38%. But the model's actually working. And then again, are your PMs subjective? Do you have PMs in your system that say check the pump, check the conveyor, check the belt? What does that mean? What do you want them to check? What should they be checking? Something like that may be very common sense for a maintenance person that has 30 years, but for a brand new maintenance person, check the pump may mean it's still there. Here was a PM. This component at a plant was checked off on the schedule as being completed the day before. So when I took the operations and maintenance people down there and they said they completed the PM on this motor, what should we have done? What should the PM have actually said? Because if you talk about this motor with the covering of dirt and dust on this motor, the temperature of the front of the bearing, when we cleaned the fan guard and cleaned the motor, the temperature on the front bearing went down 35 degrees. Now the failure rate of motor insulation is for every 18-degree rise in the temperature of that motor, it cuts the insulation life in half on the windings of that motor. So by lowering this 35 degrees, we almost got 2 times the life out of that motor. Well, almost 4 times the life out of that motor. And a simple PM task is every day, every week, we clean this fan guard off and we clean the motor off. So if we talk about training again, has your reliability and maintenance people been trained? Do they understand lubrication excellence? Do they understand the cost of effective predictive maintenance? Here's one. If we're talking about oil analysis, so many times I go into plants, they're doing oil analysis, and they haven't been trained on what the ISO cleanliness code is, what that 3-digit code actually means, and which one of the numbers we should actually be working to reduce. They haven't been trained on reading their vibration analysis results. I was at a company where the vibration analysis company was a motor company. 80% of the recommendations was replace or rebuild the motor, but about 80% of the issues were balance issues with the fan or the motor. They weren't issues about rebuild or replace. So I switched them to a normal balancing company, taught them how to read the results, and now they're actually making headway. Training people in precision maintenance. What is precision maintenance and are we using it? Using RCM method, reliability center maintenance, where we look at how components fail and we develop ways to predict, prevent, or eliminate those failures. PM optimization. This is a process. I can send you a PM optimization Word doc where you ask your own questions, but you look at the PMs you're currently doing to find out if they're adding any value. Failure modes effect analysis. If one of you need a FEMA spreadsheet where you can ask the questions and it calculates the number, I'll send you that spreadsheet to all the things you need to be doing. Developing written procedures. Me and my son are actually working at 2 plants right now. We're developing written PMs with pictures and arrows and actually explaining what the task should actually be. Now, why are they doing that? They're doing that because every maintenance person at that plant has over 35 years of experience. They're going to be retiring in the next 3 to 5 years. So these new people coming in are not going to know how to do those PMs. So the older maintenance people there are helping us write effective PMs so that they don't lose anything when these guys leave. Operations with very few failures. The airline industry. The failure rate in the airline industry in the U.S., 0.00035. The nuclear power industry. How many failures do you hear about in the power industry? Very few. The military. There's a lot of other high-risk operations in the country, but why do they have few failures? 2 reasons. They have good training programs, they have excellent procedures, and they actually follow those procedures. And by doing that, they have very few failures. And all these industries here also use RCM. And the basics of RCM is you ask the question, how can it fail, or how has the component failed? And then we ask the question, is there a predictive technology to predict the failure? Is there a PM task to prevent the failure? And is there a way to eliminate the failure by a redesign? Can we put a better component there and eliminate the failure completely? So this is why these industries, these operations here have very few to 0 failures. Can we do the same thing in the industries we're in, the plants we're in? Yes, we can. We're probably not going to get to 0.035, But what if we got all of our reactive maintenance down below 10%? How much more effective would your plant be? How much more rate would they run? Well, I have a plant in Chicago that we started 6 years ago doing these processes. Their OEE at that plant has moved from 52 to 92.3, and now they're trying to get to 96.3. What does that mean for their operation? Well, they actually produce 4.5 million units. Can't tell you what the units are because it'll give the customer away, but 4.5 million more units per month of the products they make than they were making 6 years ago. They haven't added a single person, haven't added any new equipment, 4.5 million units per month. So look at this curve. If you want to copy this curve or you want to copy this presentation, you can look at this curve. These are things you should be doing. Moving into your predictive technologies, doing these things in the proactive area. You don't have to be 100% proficient in the proactive areas, but you have to understand these processes and how they fit your system. And if you do those things, you're going to become, you can see up here, 70 to 100% efficient in your maintenance and practices, and that's going to cause your rates to go up. It's going to cause your quality claims to go down. Now this PM task in the middle here, PM tasks are going to change as you become more reliable. An example of that is, and I'll give you one quick example here, an alpha Laval centrifuge. We used to change the oil in our alpha Laval centrifuge every 30 days because the OEM said we should. When should we change the oil in alpha Laval centrifuge? When the oil analysis tells us to change it. So once we started doing oil analysis, we changed the oil in the alpha Laval centrifuge every 3 to 4 months. So your PM task changed. It changed from a PM task to a predictive technology telling us how to do that PM or when to do that PM. So again, what's it mean? The future, it's going to be dollars, right? I mean, we're all in competition around the world. We're all trying to do things to make our plants more effective. We're all trying to save dollars, and if we don't do that, you're not going to be competitive in the industry. So I don't know if we're going to have any questions. If you got questions, you have my email address on the first slide, or you can get a hold of Insight and pass the questions on. I'll get those questions answered in the next couple of days. So with that, I'll turn it back over to
me. This is
to you,
part, Terry. To Megan. So it does not look like we have any questions for this time, and that's okay, because if you do have some questions at the end of this, we can always answer them via email. But thank you all for attending the webinar today. Thank you so much, Terry Harris. In just a few hours, you all will receive an email with a survey as well as a link to the recording of the webinar today. So you all will be able to have a copy of that, and you will have that curve that Terry Harris mentioned a few times. So that's it for this webinar. Thank you so much for attending, and have a great day.